talk about weak ergodicity breaking in systems with long-range interactions. I will explain what I mean by long range here, this context. The work I will present was in collaborations with a few colleagues of mine, Aníbal Figueiredo, Marco Amato, and Raul. Zola Cynthia was my former student. In Diane, she's doing her PhD under my supervision now. Do you hear me well? Hello, 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 hello. No, there's a topological problem here. Because it doesn't fit my head well. Me ajuda aqui. Porque esse troço fica espetando minha orelha. It's okay now? Hello? Well, the point with long-range interactions is that, let me just take out this hand from here, is that if your interaction potential decays like some power of r, like 1 over r to alpha, where alpha is smaller than your space dimension, then we call this a long-range interaction. For instance, in 3 dimensions, anything that falls lower than 1 to r cubed, it's long range. So Coulomb potential is long range. Okay. What happens in this case is that if you compute the interaction, the potential in a sphere of radius r, you have to integrate something like that. There is a constant that depends on the dimension. In 3D is simply 4 pi square over 3. In other dimensions different. And you integrate this, and this potential interaction diverges if alpha is smaller than d. If you suppose a homogeneous distribution, for instance. So the interaction potential of particles very far from the origin are even more important than particles near the origin, near where your particle is located. So you have the interaction potential between parts of the system is very important. It's at least so important as the bulk energy when you divide the system in 2. So this implies a lot of special behaviors. I will explain some of them here today. Some obvious examples are self-gravitating systems with a Coulomb interaction. For instance, you can have galaxies as your point particles, or stars, for instance, in a galaxy or in a globular cluster like this one here. And these are some obvious examples in nature. Charged plasmas, of course, also. And some other systems, like interactions between point vortices, like the vortices here in Jupiter, in a 2-dimensional systems. There's this model by Onsager, where the interaction is logarithmic between the point vortices. So you have also something like a long-range system. Surface quasi-geostrophic dynamics, etc., and some model in mantle convections. So you have some models that you can consider as long-range interacting. In other models, like, of course, charged plasma, wave-particle interactions in plasmas, where particles interact through a wave, one mode or more modes. So this is also this kind of model. Some spin models, some simplified models that we'll speak here, the ring model, HMF model, 2D and 1D self-gravitating system. And of course, there's a special case, small systems, where the size of the system is of the same order of magnitude as the interaction. So you can have similarities for this between all these systems. And long-range systems may, not always, may display some different behaviors. First of all, they are non-additive, in the sense if you cut the system in half, your total energy is not just the sum of the energy of each part, because the interaction energy between the 2 parts is not negligible in this case. Okay? This has also a very complicated consequence that entropy also is not additive. Just a small remark, this has nothing to do with non-extensive statistical mechanics, but if you cannot add the energy, you have contributions of interaction energy, the same will happen with your entropy, okay? But the form of the entropy is the usual entropy, Boltzmann or Gibbs entropy. You can have negative heat capacity in some cases. If you take a self-gravitating system, this is a direct consequence of the dynamics of the virial theorem. You can show that the total energy equals minus the kinetic energy. So if you derive your total energy with respect to temperature, you have a negative number. It is well known in astrophysics. It doesn't violate the second law of thermodynamics because your entropy is always maximum. The point is that the system, when you separate the system, you cannot speak of energy of each part separately, but as a whole. As a consequence, you can prove that in the canonical ensemble, heat capacity is always positive. It's a very simple proof that derives from the Boltzmann factor. So, for gravitational systems, the microcanonical and the canonical ensemble are not equivalent. Even more, your system cannot exist at equilibrium if it has a negative heat capacity when you put it in contact with a heat bath. It just cannot, because it's unstable then. But if it is isolated, it can exist in such a state. This is another interesting consequence of the nature of the long-range interactions. In the canonical ensemble? Yes, you can. Of the heat capacity. You just compute the average and derive it with respect to temperature. If you use the Boltzmann probability, the exponential minus beta E, and so on. Yeah? In the canonical ensemble, it's always positive. You can only have negative heat capacity if in the microcanonical ensemble. So the prescriptions of microcanonical ensemble and canonical ensemble are different in this case. All proofs we have of the equivalence of Gibbs ensembles always rely on the short range of the interactions. You need this to prove that they are equivalent. You have non-Gaussian stationary states. I will show one example. These states, they have a lifetime that depends on the number of particles. This lifetime is very big and diverges with n, the number of particles. Okay? So in the thermodynamic limit, these non-Gaussian states are the final state of the system. So I will come back to this here. And you have something known as violent relaxation, which causes some phase mixing, in the sense that you start from a non-equilibrium state, it rapidly goes to this quasi-stationary state, and then you stay in this state for a very long time until you finally, if n is finite, after a very long time you relax to true Gaussian equilibrium. And they can be non-ergodic. This is the main part of the talk. So we have essentially these three evolution states. The first one, very fast, which we call the violent relaxation. Then a quasi-stationary, usually non-Gaussian state. And finally, for finite n, the thermodynamic equilibrium. I will show, of course, it's always good to deal with some toy models to discuss the physics, but these issues are present also in real laboratory models or in astrophysics. The first one is the ring model. Well, the idea is to take gravitation-like interactions between two particles and which are constrained, all the particles are constrained on a circle of a given radius. So the distance between the two particles are given by 1 minus the cosine of the difference of the position angles. And by just choosing the units, I can write the Hamiltonian of the system in this way. Of course, P here, the momentum is the angular momentum of the particles on the circle. The 1 over square of 2, this is just a choice of units. This small epsilon is just usually a small parameter that you may encounter in many astrophysics simulations to avoid the divergence of the force at 0 distance, because otherwise you cannot put this on a computer. And this factor 1 over n is called the Katz factor. You can think it is also a choice of units where you change your unit time by square of nt. Then you make appear this factor here, and this is well defined and provided that n is finite, of course. It has the advantage that now your energy, which is non-additive, because if I cut the system in 2 halves, the energy is not the energy of one part plus the other, but one plus the other plus the interaction between the two, which is of the same order of magnitude, usually. And in this way, here the kinetic energy is proportional to n, and this double sum is proportional to n squared. If we divide by n, you have something proportional to n, and your energy is extensive. It simplifies the description. But we could do the same thing without this factor, if n is finite. And the Hamiltonian mean field limit, which has this Hamiltonian, you can think it, obtain it, in 2 different ways. First, by consider a big epsilon, if you want to play, and take just the first correction. Or it can derive from one-dimensional gravity if you expand the potential in Fourier modes and take just the first mode. But it's a toy model. It has some interesting advantages. It is exactly solvable at equilibrium. I can compute the partition function exactly, the equilibrium distribution function. For numerical simulations, the numerical effort scales with n, because you can compute the force by this expression, simply compute the gradient here, where mx and my are the, in fact, there's a 1 over n missing here, is the average of the cosines and sines, and we call this the magnetizations by analogy with magnetic systems. So it's very, and it has a phase transition from a non-homogeneous to a homogeneous state. The ring model also has the same phase transition. And just to show main difference in the dynamics, which is I am interested here today. Here I will show a simulation of this Hamiltonian, which is very similar to the HMF model, except that the interactions are to just the next. You can think these as rotors on a line, and each rotor interacts to its first neighbors on the left and on the right, which give this expression. The simulation with 10,000 particles, and well, the evolution is the one we expect. So the initial state was here. I have the position on the vertical. I have the momentum. So I started all the spins all aligned in the same directions. Then it evolves slowly, very rapidly to the Gaussian thermodynamic equilibrium. And if I take an histogram of the particle velocities here, I will have a Gaussian distribution. You see, then this is the equilibrium. The particles are moving left here because, and right here is just the. It's homogeneous at the end. Here it is here's the space, and here's the speed. Okay. So it's you have a Gaussian distribution of velocities and a homogeneous space distribution. I will show you that. And I will take this is the HMF system, the same initial conditions, the same orientations for the spins, and what I call a water bag distribution. That means a uniform distribution So I have the same initial probability for the momental velocities. Well, this was solved using a symplectic integrator. It is. And we see this is very different from the previous case. The system retains the memory of the initial states for very, very long times. Here I have 10,000 particles. 10,000. And what's happening? It is evolving towards, this is the violent relaxation I spoke before. It's evolving towards a quasi-stationary state. You see, it still retains some memory of the initial state for very, very long time. Yeah, almost there. Because you go to these quasi-stationary states, but you can keep some oscillations, like you have in plasmas, and these oscillations will damp with time, with something similar to Landau damping. But you have these structures here, you see, for instance. These structures. In the sense, yes, but you keep, if you compute the correlations functions, for instance, you'll see they will decay much slower than for a short-range system. You can define memory in other way. But the system is chaotic, by the way. But you see, the point is that, let me continue. It preserves memory also. Oops. No, sorry. It's compiling again, but it's okay. Let me just... let me go on. It crashed, that's all. Here. The first stage, if n is very big, which is usually the case in these systems, we can show that a Hamiltonian system with a long-range interactions with a Katz factor of this type, you can describe the statistics of the systems by the Vlasov equation, which is an equation usually seen in plasmas, which essentially says that in one particle phase space, the total derivative of the one particle distribution function is 0. Then you have this equation, which is the Vlasov equation. F here is the force, which is the derivative of P, is the mean field force, in the sense that it is here, this mean field potential is the statistical average of the potential at point R, considering the particles at point R prime. Here is pi prime and P R prime. Okay. If n is finite, here instead of 0, we'll have a collisional integral, collisional term that gives rise to a kinetic equation like a Landau or Lenard-Balescu equation, Balescu-Lenard equation. Okay. So this the Vlasov equation, it has an infinite number of conserved quantities, in the sense that any function of the distribution function, one particle distribution function f, if you integrate over the whole phase space, gives you a constant of motion. And in this, no, it's Vlasov equation, or collisional Boltzmann, they call it that way also in astrophysics. This is the Vlasov equation. Sorry? Yes, you can, for instance, no, because, let me explain. You take any function of f, rpt, then you integrate this in p and r. This gives you some function of t, okay? Because you have time here. C is any function. We can show that f dot is 0. That's a Casimir. So you can choose, for instance, f log f. That's the entropy. The entropy is constant for the Vlasov equation. That means this equation is reversible. If you reverse time, you come back to your initial state. So in order to this derivative not be zero, you must have something different from zero here. You must have collisions, collisional corrections. If you don't have collisions, your evolution is collisionless. So the first, of course, if n is finite, you will have small collisional corrections that drive very slowly your system to equilibrium. Okay, but if you are in a thermodynamic equilibrium, your equation is reversible. You don't lose memory. Oh, well, this will be certainly system dependent. Yes, it has physical consequences, real physical consequences. No, not irrelevant because it has implications in the dynamics of the system. Yes. Yeah, in this sense, yes. But they are important to the properties of the system anyway. Yeah, in the sense, yes, okay. So this is just a simple example of the solution of the Vlasov equation, a numerical solution. In this case, 1D, gravitating systems. I will come to them later. So I start with, this is a uniform distribution. Here I have the angle, here the momentum, and it is uniform here. It evolves. One of the Casimir's you can construct and show it has a consequence is that this area here, the value of f is preserved because f dot is 0, and this area of this figure is preserved. So if I take this figure and this one, the area is exactly the same for the Vlasov equation, okay? So it evolves, it creates some filamentations like I see here, and this, of course, at some moment your numeric grid, you lose enough resolution to describe it, and you have something like that, which is this is the quasi-stationary state, which is clearly non-Gaussian in velocity. It's an example. Yes. In this case, it is this kind of Hamiltonian system, this particular type, with long-range interactions. They can be described, its statistics, by yes. Yeah, there's a theorem. Well, this is a long discussion, but I think it's an approximation. If n is finite, yes, but not in the thermodynamic limit. Then it is exact. Yes. If you do Hamiltonian dynamics with enough particles, I have done that, don't have the figures here, and you display the histograms, it will have the same appearance. So what's the... No, this one is the initial condition. This is the time evolution of this initial condition. Solving numerically Vlasov equation for the system. Yeah. You can take a look at Brown and Hepp, this paper. For this type of system, okay. So let's go to our point is ergodicity, which essentially simplifying it a little bit, that you have time averages are equal to ensemble averages. You can have also strong and weak ergodicity breaking, in the sense strong breakings when you have some region of your energy hypersurface which are not accessible by the system. Here it is always accessible. So if time averages are different from ensemble average, in all your energy hypersurface is accessible. I call this weak ergodicity breaking. Here I have an example for the previous HMF model. 3 different particles for a water bag initial condition, how they evolve in time. So this is a very long time. I hear it is 10,000 time units, which is quite long. They have a very different history. If you take a short-range system, you see that each particle very rapidly has a Gaussian distribution for its velocities along the time. Here, if I do an histogram for the velocities of each particle, they will have very different histograms. So for all particles to have the same distribution of previous velocities, you have to wait a very, very, very long time, which is usually the time you take to equilibration. Okay, this has to do with ergodicity. I will show you, I use essentially 3 different ways to try to assess if the system is ergodic or not. The first one is based in the idea I just discussed in this figure, is to take the time average velocity for a given particle. Pi is just, I do this in a computer, delta t is the time step, so I just keep summing the velocities of each particle or the momentum. The mass here is 1, and I divide by the total time, so I have an average particle I. So here, each particle has a different time average. I have 10,000, 1 million. I can do this with... Yes. No. No. It depends on the time window. I'll get there. It depends on the time window. Yeah, yes, that's the idea, precisely. So I take and then I compute the standard deviation for this new stock variable. Just the usual. Yeah, standard deviation, the variance. And then I can take a look what happens. I'll show some systems. The second method is what we call sojourn times. It's based on a work by Hebenstock and Barkay, which is not here yet, unfortunately. So we consider the dynamics as a continuous time random walk, as if it is. And we divide the phase space in a certain number of cells. Bigger or smaller, we can choose that. And the sojourn time for one state, one of the cell K, during is the visitation of number J, is denoted by this, TKJ, the sojourn time. When I visit cell K, the jth time. So the residence time in that cell is just the sum of each sojourn time. And we take any observable and compute its time average as the value it takes on a given cell times the value of the observer in that cell. And the total time is given just at the sum of all visitation times. And suppose that the sojourn times are independent, identical distributed variables, and use the central limit theory, the probability distribution of residence time can be described by one-sided, of course always positive, because times here are always positive, one-sided Lévy distribution, which is given by this Laplace transform. And if alpha goes to 2, we have the usual Gaussian distribution. We have, of course, this distribution is such that the moment of order mu diverges if mu is bigger than a, alpha. And that's the result by Hebenstock and Barkay, that the distribution of possible different values of the time average is you can have in the system given by this complicated expression. And if alpha goes to 2, this distribution is this one where this value is the ensemble average, Therefore, your time average equals ensemble average, and then your system is ergodic. If not, if alpha is different from 2, you don't have this result, and the two averages, time and ensemble, are different. Okay? Want to ask so? Okay. Where the ensemble average is just, the gamma is the size of the cell, so it's the size of the cell, essentially, with a normalization. So it's a measure of the cell. If your cells are equal in size, it's the same constant. You have just, it will become a normalization constant. Well, the truncated Lévy distribution has some, which I speak here, but I spoke of the Lévy distribution, anyone here knows, but I can truncate the distribution because in a real system, you cannot have a state with an infinite deviation. Usually what you have is a Lévy distribution up to some point, then it falls to 0 very rapidly. So we can, this was introduced by Mantegna and Stanley. The idea is your distribution is the Lévy distribution with index alpha in some interval. Here's just a normalization constant, and 0 outside this interval. So you just do a sharp truncation. And if you have this, I can compute the probability, I can add random numbers that has this truncated distribution. Then, of course, your second moment in this case is always finite. Then this distribution must, in the limit, go to a Gaussian distribution if we sum a very large number of stochastic variables with this distribution. The point is how long it takes to go, how many terms I must have in the sum, such that the distribution of the summed variables is sufficiently close to a Gaussian. That's the point Mantegna and Stanley addressed. So in order to, usually the sum takes, it converges very slowly to a Gaussian. It goes to Gaussian because it's the central limit, the classical central limit, but the point is the velocity of convergence. So to study this, you can compute here the probability of return to 0. That means that if I add a given number of variables, what's the probability for you to be at 0? The sum to give 0, or at least something in a very small interval around 0. You can show that this it is given for Lévy distribution is essentially proportional to 1 over n to 1 over alpha. And if alpha equal 2, I have this, which is the Gaussian distribution. The other things are just constants. And the index is 1/2. And this is valid for n very small to a crossover value, and this one is valid for n bigger than a crossover value, which is essentially proportional to L alpha, the power of alpha, and here is not L, is D to the alpha, where D is the truncation value. So if D goes to infinity, this n cross here goes to infinity, and we always behave like that. If D is finite, then you start this sum to 0. If n is small, it has a slope like 1 to the minus 1 over alpha, then it goes to 1/2. So if I have numbers, a series in a computer, I can do this test to see if the distribution is a Lévy or not. And if alpha here is 2, then I have ergodicity. That means I take my phase space, I divide in cells, I compute the sojourn times in the computer, then I apply this test here and extract the value of alpha. And I can see, I will show, and I can see this crossover. The value of the crossover, it will depend on the number of particles. So this is another way of testing ergodicity in the system. Well, and the third one is what we call the dynamical functional. This is based on a work by Janik and Veron, and Cambanis, Podgorski, Veron, Maxiars. I don't know how to pronounce correctly. Yeah, I will show the result. Okay, you can do that. Yeah, if, I have access to all numbers. Yeah. Yeah, I'm speaking here distribution of sojourn times. I will show you the result and we can discuss it. So the test is very simple. You define, I will simplify here. I don't know how, I'm taking too much time. You define the dynamical functional for a stochastic stationary infinitely divisible process, stochastic variable y. Realization has a value yn. Then I define this function as the average over the different realizations of the value of y at step n minus its initial value. Here I consider yn as simply the value of the momentum of particle k at time n delta t. So when I take this average, it's taking the average over all particles, okay? I will look, I can do this for position variable also, of course. And the system, the test is this one. The system is ergodic if this function, the limit of qn, which is defined by this expression, is equal to 0, and it's mixing, then I can text mix also, if this limit here is 0, where en is dn minus the value of the exponential p0, ensemble average, etc., etc. Okay? So, let's go to results. This is the HMF model. Here I show, this is the direct method. So remember, this is I take the time average of each particle velocity and take the standard deviation for overall particles. So here I have 1,000, 10,000, 50,000 particles. The time here is 10 to the 6th, 1 million. This is the standard deviation of the time average of the velocity of each particle, the average taken over the n particles. So I take each particle, it has a time average from 0 to time here. Take this time average, I do it for every particle, and then I take the standard deviation for these numbers. Sorry? Yes, that's divided by the number of particles, of course. Yeah, yeah. No, you have. So what happened? What the point here is to show that they usually tend to 0. You see, they diminish over time, but it takes a very, very long time. And clearly, that if you augment the number of particles, here's 10,000, here 50,000. The time to reach 0, it tends to augment. So I should have to even further. This takes a very long time. No, wait, no. Yes. Now, if you take this value here, and here, this certainly goes 1 over n. No, this is time here. The slope, it doesn't need, you see, this time. The number of particles is the different color, okay? Yeah. Now here, sojourn times for the HMF model. Let me explain. Here is the value of the sojourn time. Here is the distribution function of these sojourn times. You see? And we can see that there's well, of course, the statistics is limited. On the left panel is 50,000 particles. This is just energy, average energy per particle. The size of the cell I choose in momentum space, 10 to minus 2. The total integration time is 10 to 7. The right panel, the same, but the cell was just 4 times bigger to compare the effect of the size of the cell on this distribution. And here I have in both axes a logarithmic scale. So we can suspect that this seems to be some linear behavior, but it's always very difficult to see if you have a tail which is algebraic or not. That's why it's good to do this test of probability of return to 0, to see if this corresponds really to a one-sided Lévy distribution or not, and to see if the system is ergodic or not. So this is what is done here. This is the probability of return to zero. In fact, here, what I do, at some time, I take all velocities particles. I have this on the computer, and then I can shuffle them. Okay? And then I can add. This is for the final time. Just one fixed time. I evolve the dynamics. I have all particles velocities. Then I can shuffle them randomly and add them as random variables, okay? And do this, do a given number of realizations and do the average, just to have good statistics. And then I can, when summing these random variables in this way, I can see what's the probability that the sum gives zero. In practice, I choose a small epsilon, and I see for the sum if I am in this very small interval. Not exactly zero, because it's impossible. When doing this, this is what I obtain for 10,000, 50,000, 100,000, 200,000 particles. So as the number of particles augments, you see you stay to this line, which is an algebraic law, a power law, with alpha equal to 0.603. On the left, I prepare the system in equilibrium. Because the system is solvable, I can use a Monte Carlo or Metrop's algorithm. I put the system at equilibrium, I'll obtain this value. And here is for a water-back state, which is chosen to be a quasi-stationary state. You stay in the state for a very long time. And here the value of alpha, 0.51. No, it's not, I cannot read. It's the power law. No, alpha, no, sorry, alpha is the, because you remember, for a Gaussian distribution, you must have 1 over n 1/2. Okay? 1 over alpha. And alpha must be 2. So alpha here is 0.603, 0.51. So it's very different from 2. But this line is the niche, is you add your variables, you stay on this line, then you go, and here the slope goes to 1/2, which means a Gaussian distribution. So you variables, and as the central theorem tells you, you tend to the Gaussian distribution, okay? And but the number of terms I must sum augments with the number of particles. So what happens? Your system, if you wait a sufficient long time, which is like 10 to the 7 here, the total simulation time, it becomes ergodic. But you have to, the time observation, the time window for observation must be very, very big, and this time augments with n. So if you go to n goes to infinity, most certainly you always stay on this line. Your system will never be ergodic, which is, of course, natural, because when n goes to infinity, this state, this quasi-stationary state, it doesn't relax to equilibrium. But here, even if you are in equilibrium, you put the system, because you don't evolve to equilibrium, you just put it there already. It stays there and is non-ergodic. Yes. Yes, because this quasi-stationary state that you evolve depends, because of the Casimirs, they depend on the initial condition. A different initial condition gives you a different quasi-stationary state, but if the energy is the same, the final thermodynamic equilibrium will be the same, of course. But the path it takes to get there is different. Ooh, that's yeah, this is a complicated question. You see, because I have a similar. Yeah, we can discuss this later, because I have another work. This has to do with Lyapunov exponents, how they behave in this limit. Because this is a problem, I think, of non-homogeneous limit. Yeah, yeah. But here I have in no, here the system is in equilibrium for the is Gaussian. I put it with a Gaussian distribution. Here not, but in both cases non-ergodic anyway. This is the I just look at the how the space is visited. Since this is showing that your time average is not equal to your ensemble average, and the ensemble average, of course, is the all states are equiprobable. Here I'm on the microcanonical ensemble. The system is isolated. Okay. This is the second moment for sojourn times for the equilibrium and water-bag state as a function of n, and we see that they tend to diverge, although it's still finite, but it augments. This has to do with the fact that probably I have something like a Lévy truncated distribution, and the truncation goes to infinity when n augments. There's an indication of that. This is the dynamical functional method. This is the third method to test. So here is Q. This one is E. This tests for ergodicity. This one tests for mixing, and you see that they really tend to small values. It's very difficult because here the simulation time must be very big. Here's for 1,000, 10,000, 50,000 particles, so they tend to 0. Here I have a lot of noise, but we see at least for 50,000 they really tend to 0. This is also an indication that the system is ergodic, but as the number of particles augments, you see the time window I will need for it to be ergodic also augments. So the conclusion, at least for this system, seems to indicate that when n is finite, the system is ergodic and mixing, but for that your observation time must be very big, and this observation time augments with the number of particles. And in the thermodynamic limit, it becomes non-ergodic and non-mixing. This one's for a water bag, non-equilibrium state. This one is a Gaussian state, is essentially the same. Some results also for 2D and 1D gravity. How much time do I have? Okay, I would try to go far, just show the results. The idea is to study, this is 2D gravity. The potential is logarithm because it's the solution of the Poisson equation in 2 dimensions. The force is 1 over r here. And 1D gravity, the potential that is solution of the Poisson equation is just the absolute value of the distance. This is equivalent of infinite planes of equal densities, like capacitors, but with attractive forces, okay? Always. And I can study this state also in the homogeneous state, this system homogeneous state, by just reproducing the physical cell infinite times and doing what we call the Ewald sum, which can be exactly summed. So reproducing the periodic conditions is equivalent to introducing this potential. Xc is the position of the center of mass on the unit cell, and L is the size of the cell. For 2D gravitating system, note here that in both cases I put this 1 over n Katz factor, okay? No, this is gravity. On the plane, infinite plane, and the line is the HMF model. Huh? Is what do you mean? Yes, this is the HMF model. Now I changed the model. SOTA, yes. Now, SOTA is the ring model. There is yes, it was that one. Now is gravity, really. So the potential is solution of the Poisson equation in 2D in 1D. It's different from previous. Yeah. And if I introduce this Ewald sum, I can do periodic boundary condition and study homogeneous state. Well, for 2D, here I go from 64 to 16,384. Here the simulation is very expensive because the simulation time goes with n squared before it was with n. So this is done on GPU, etc., in parallel. So what is interesting here is the functional method. This is the direct method. Is the standard deviation for the time average of the velocity of particles, and they all follow the same line. And here is the kurtosis of the distribution that shows you to the equilibrium value is 3. So you go very, very slowly to equilibrium, but still this is a quasi-stationary state. This one is for the 64 particles. With a bigger number of particles, it is almost horizontal here. And we see that the time it will take to go to 0 is the same. But since I changed the time units with this, I can say that the time window in the original units, the time window to observe ergodicity, it goes with the square of n. It augments with the more or less with the square of n. This is the times for 2D gravity. Oops. This is just this one I can simplify. These are the functional method, Q of n and E of n, and we see that it goes it's still not really 0, it goes a little to below. Here is for 512 particles. And even then, A and B is real. No, sorry. The continuous line is the real part, because it's complex number, and the dashed line is the imaginary part. Here is 128. Here 512, they have a similar behavior. They usually tend very slowly to ergodicity. Also, we can, in 1D, just to finish, I consider here a homogeneous state. I first left the system go through this violent relaxation and fixes in this quasi-stationary state. I have 512 particles or so. Here's the dynamical functional, and I cannot see any tendency to go to 0. Here's an homogeneous state using the evil sum. Here's the test for ergodicity. It goes to a value, and here is this is for the mixing. See, in mixing, it stays really close to 1. It has a very small tendency to go down, but I think this is due mostly to numerical errors. And I have the conclusions. This case is very interesting because I believe, I am trying to show this with my student Lydiane, this system has a peculiarity. And for that I have to show just rapidly Hamiltonian. If I look at this Hamiltonian here, the force between two particles is constant, and it only changes when they cross each other. Or if you prefer, we can relabel the particles and say they collide, like rigid dots, and just exchange velocities. But before that, force is constant. So between any two collisions, the system is integrable. Okay? And what the collisions do is just swap velocities. So collisions cannot change velocity. It's like a homogeneous hard sphere gas, which has no dynamics. So I think this system also, it cannot, once you are in a stationary state, it has no dynamics. So it is exactly non-ergodic. I'm trying to prove this more precisely. But before you are in a stationary state, you have this collisionless relaxations obeying Vlasov equation. And then the system is not, but once it settles, after some Landau damping, it settles to these quasi-stationary states, there's no more dynamics, apparently. And you can see this in numeric simulations. If you diminish you take a time step, you take a smaller time step, what you see that this small tendency we observe here, it so diminishes. So it's then conclusions. Ergodicity and mixing can be studied in long-range interactivity in some different approaches with compatible results. They are ergodic in mixing for finite n, but for a long observation time window. In the fluid limit or in the Vlasov limit or thermodynamic limit, if n goes to infinity, the system becomes non-ergodic. And into the self-gravitating system, I have a pathologic dynamic, seems always to be non-ergodic even for finite n, but this is still an open question that I hope to prove soon. And thank you for attention. Yes?